So, let us quickly recall Noether normalization. Let R be a finitely generated K algebra. Then there exists variables, algebraically independent elements. Z1 up to ZR and R such that K Z1 up to ZR injects into R, and R is a finitely generated. So, let us call this S module. So, I mean we proved this when the field K is infinite. I am not going to repeat the proof, but I will quickly go through the steps. So, here what we did was we proved this by induction on n, but what is n? I am looking at. So, when I write this k x1 up to xn, I mean R is a K algebra generated by x1 up to xn. These need not be variables. If you have confusion, yeah, okay. I will just simply write like this. See, for example, we discussed this over k. So, if I look at this K algebra x1 x2 minus 1. So, this I can write as K algebra generated by x1 bar x2 bar, right. Now, this is, see, x1 bar as it is algebraically independent over k, because it does not satisfy any equation over k. Okay. But now, if I look at this one, x2 satisfies an algebraic equation over k x1, which is x1 x2 minus 1. So, if I look at this x1 bar t minus 1, this is a polynomial. No. So, this is not integral. Okay. This x2 satisfies a polynomial, but does not satisfy an integral equation. The extension being integral, one big advantage of extension being integral is that the dimensions are same. Yeah, it will be finite first of all. Secondly, it will the dimension of A. So, if I have an integral extension A contained in B, so we defined the Krull dimension, right, maximal length of chain of prime ideals, right. So, if this is integral, then Krull dimension of A is same as Krull dimension of B. Okay. So, in this case x2 is not integral over this ring, but it satisfies an algebraic equation. So, when I write R equal to this form, I mean x1 up to xn are generators of R over K as a K algebra. They need not be algebraically independent. Here x1 bar and x2 bar are not algebraically independent. That is one remark I wanted to make. Now, so how did we prove? we proved, first of all, if x1 up to xn are algebraically independent, we are through. We can just take R to be equal to n itself. Okay, we do it by induction on n. If n is 0, you can take R to be 0. Suppose n is bigger than 0, if they are all algebraically independent, we can take R to be equal to n and zi equal to xi, and we are through. Suppose we have a polynomial which is satisfied by this. We look at homogeneous component of all the homogeneous components of the polynomial which is satisfied by this. Then we look at the leading homogeneous term, that is the homogeneous term of highest degree. Now what we do is that we make coordinate changes so that this becomes a monic polynomial in one of the variables, say xn. So how do we do that? Given a homogeneous polynomial, we proved that lemma saying that there exists an n minus 1 tuple such that f it does not vanish at that, which is not a root of the given homogeneous polynomial. Okay. There we use the fact that the field is infinite. For that part we need the field to be infinite, otherwise we can't really say this. Okay. So that using the fact that it is infinite, we convert the given polynomial into a monic polynomial, and that gives me the, I just change the tweak the generators and get in a slightly new form y1 up to yn, such that they satisfy the same polynomial which is monic as a polynomial in yn. So therefore what we get is that yn is integral over k y1 up to yn minus 1. Now k y1 up to yn minus 1 has only n minus 1 generators as a k algebra. Therefore we can apply induction and say that there exists variables z1 up to zr such that k z1 up to zr injects into k y1 up to yn minus 1 and the extension is finite. Now k y1 up to yn minus 1 to k y1 up to yn, it is again finite because it is integral. Yn is integral over k y1 up to yn minus 1. Therefore we have k z1 up to zr to r is finite. Okay. That is how we proved the Noether normalization lemma. So as a corollary to Noether normalization lemma, we prove Hilbert's Null-Stellenza Null-Stellenza in German, this is German word meaning theorem of zeros. Okay. So there are 3 forms. We will be discussing 3 forms of Null-Stellenza. So the first form is called weak form. This says let R be a finitely generated K algebra which is a field if let R be, then K over R is a finite field extension Moreover, if K is algebraically closed, then K is equal to R. So, what this says is that if I have a finitely generated K algebra, which is a field as well as finitely generated K algebra, it has to be a finite field extension. Finite field extension means as a vector space over K. See, finitely generated C x1 x2 mod x1 x2 minus 1, this is, so if I write this as C x1 bar x2 bar, if this, I mean this is a finitely generated C algebra, but this is not a finite extension C, this is not a finite C module, because you have many more algebraically independent elements here. See, if I take x1, x1 square, x1, I mean images of 1 bar, x1 bar, x1 bar square, these are all independent over C, right. There is no polynomial that this x1 up to say xn, I mean x1, x1 square, this set satisfies over C, not over x1, x2 or anything. Over C, this is a linearly independent set. So, therefore, this is not a finite field extension. I mean, of course, this is not a field, but this is not a finite module, I am saying. So, here the situation is, if R is a finitely generated K algebra which is a field, then there are no other option. I mean, it has to be a finite field extension. I mean, the second part follows directly from here. If K is algebraically closed, which means you cannot have any finite field extension of K, which means K is equal to R. So, first let us prove this part. So, R is a finitely generated K algebra. Now, we have this Null-Stellenza which says, by I mean we have the Noether normalization which says there exists Z1 up to ZR such that K Z1 up to ZR is contained in R. Now, R is a field, okay. So, I have K contained in K Z1 up to ZR contained in R. Now, R is a field, and this is what we indeed proved is that this is an integral extension. This is a finitely generated module over this one. Therefore, and this is a field, therefore, this is also a field. This we proved some time back. I mean, this what we indeed proved is that this is an integral extension, right. The proof of Noether normalization says that this is an integral extension. By induction, we proved at each step you can get an integral extension. This is integral, this is field, therefore, this is a field. How can this be a field? The only way is R is 0. A polynomial ring Kx, this can never be a field unless, I mean Kx, no this one Kx1 up to xn can never be a field unless n is 0. So, therefore, this implies that K Z1 up to ZR is a field. what does that say? That says that R is 0, that says that k to R is finite. Okay. Now, if R is if k is algebraically independent, algebraically closed, then R is then k does not have a proper finite extension. And that implies that k is equal to R. It can have infinite extension. For example, C, the field C, it is algebraically closed. You cannot have a finite extension of C, but you can still have like this, right? You attach a variable. This is an extension.
So why not finite?
Finite will imply algebraic. You cannot have any algebraic extension of C, right? You cannot have a algebraic extension of C. In particular, you cannot have a finite extension of C, but this is neither algebraic nor finite. So, similarly, what here if k is algebraically closed, R has to be equal to k. Another very important form of null stellenza is the one which describes the maximal ideals of polynomial rings over algebraically closed fields. So, look at let us look at another form. This is another corollary. Let k be algebraically closed. Then the maximal ideals of k x1 up to xn are of the form x1 minus a1 up to you must have seen the one variable version of this in say for C. If you look at the polynomial ring Cx, maximal ideals are always of the form x minus alpha, alpha varies over. But now this theorem says that maximal ideals of this are precisely the maximal ideals, precisely the element ideals of this form. So, let us prove this. Let I be a maximal ideal k x1 up to xn. Okay. Then I have this map k injects into k x1 up to xn modulo I. Okay. this is the map is AI mapping to AI bar. For any K algebra, K sits inside the K algebra in this form. K is a field. So, this map is always injective. If it is non-zero, it has to be injective. If I is a maximal ideal, this map has to be non-zero. Therefore, it has to be injective. So, this K sits inside this in the natural manner. But now, what we know is that I is a maximal ideal. Therefore, this is a finitely generated K algebra which is a field. By the weak form of Null-Stellensza, it says that this is a finite extension, a finite field extension of K. Since this Kx1 up to xn mod I is a field by Hilbert's Null-Stellensza weak form, so let me call this R. R is a finite field extension of K, but now K is algebraically closed, which means K has to be, R has to be equal to K. Since K is algebraically closed, K has to be equal to R, or this K has to be, I should write K has to be isomorphic to R. K sits inside here, that image has to be equal to R, or in other words, AI, the map AI going to AI bar in to R is an isomorphism. That is what it says. Now, if I take, so I have this K x1 x2 up to xn x1 bar. So, I write this as K x1 bar up to xn bar. Okay. So, let me call this map phi. Let AI be equal to phi inverse of xi bar. This is uniquely determined. Okay. Then what would be the so that says that the ideal I is precisely x1 minus a1 up to xn minus an, because a1, see in this one, if AI denotes this, x1 minus a1 has to be 0 in x1 minus a1 has to be 0 in R. Similarly, xi minus ai has to be 0 in R, or in other words, x1 minus a1 comma xn minus an is contained in I, but this is a maximal ideal. X1, the ideal generated by x1 minus a1 up to xn minus an is a maximal ideal. Therefore, they have to be equal. Let me, this implies that xi bar minus ai bar is 0 in R, which is K x1 up to xn modulo I. That implies that xi minus ai is in I for all I from 1 to n. That implies that the ideal generated by these elements, this is contained in I. Now, this is a maximal ideal, I is maximal, is a maximal ideal, they are equal. That is precisely what we wanted to prove. Every maximal ideal is of this form. Now, the third form of Null-Stellenza talks about how how closure of a variety looks like, or in other words I will so given a set X in A and K, okay, I can go to the polynomial ring by looking at I of x, the ideal in K x1 up to xn, right. Now, given an ideal I in the polynomial ring, I can look at all the common zeros of I, V of I. V of I is set of all A1 up to An in Kn, in fact A and K you can say, such that f of A1 up to An is 0 for all f in I, all the common zeros. So, if I start with an algebraic set, I can get an ideal and then come back here, okay, I go back to this one, I again land up with a set here. I start with an ideal here, I come to this one to get a set in A and K and then go back to get an ideal here. What are the relations between these two? So, if I start with, let us start with an element x in A and K, okay, and then get an ideal Ix and then go to V of I of x. Can we say some relation between them? X is contained in V of I of x. Can we say that these two are equal? Okay. So, let us let's look at the other one. I start with an ideal I in K x1 up to xn. I have V of I, which is a variety in A and K, and then I get back to I of V of I, sorry, K x1 up to xn. Let's start with a simple example here, okay. Suppose I take x, suppose I take the ideal x square, okay. What is, so x square in K x, what is the 0 set here? All elements which vanish on all elements of ideal. What would be V of I? Zero only, right? Vi will be 0 only. That is the only element which will vanish on every element of this. Now, what if I go back I of 0? I am looking at, now I am looking at all the polynomials in, forget about this what we started with. Now I have this set, I am looking at all polynomials in Kx which vanish on 0. All polynomials with constant term 0. Which is the ideal generated by x. So, what is the relation between these two? This ideal is contained here, and what is the exact relation between these two ideals? Can you give me a precise relation between these two ideals, ideal generated by x square and ideal generated by x? Yeah, or in other words, radical of this is this, and that is precisely what the Hilbert-Snell-Stellenza says, that you start with an ideal, form variety, and then take the ideal of that variety. What you get is nothing but the radical of the ideal that we started with. Okay. We first prove a slightly more general form. Let R be a finitely generated K algebra then for an ideal I radical of I. So, we have already seen the definition of radical. It is the all elements with some power of the element contained in I. We then proved that it is nothing but intersection of all prime ideals containing I. But now, in this specific situation that ideal I is contained in a finitely generated K algebra, radical of I is nothing but set of all maximal ideals containing I. Okay. So, in this one inclusion is clear, right? This is contained here, right? Clearly, radical of I is contained in the right hand side. Now, what we need to show is that if there is an element which is not here, I want to say that there exists a maximal ideal that misses that element. Okay. So, let f be not in radical of I. That means f power n does not belong to I for all n. Or in other words, if I look at this set f power n, n from 0, 1, 2 and so on, then S intersection I is empty. So, consider the ring S inverse P maximal in S inverse R. Okay. I look at the ring S inverse P, consider the ideal S inverse P, maximal ideal in S inverse R. Okay. And P is prime, and see the correspondence between prime ideals of S inverse R and R. We already know that they are all prime ideals that do not intersect with S. So, therefore, this is a prime ideal where P is a prime ideal in R. Now I claim that P is indeed maximal in R. Suppose I prove that P is maximal in R, okay, that would say that F cannot be in P naturally, because F is in S. This F, this is in S. If I say that P is maximal in R, S inverse P is maximal ideal. Okay, if P is maximal in R, I have obtained a maximal ideal which do not contain F, and that is exactly what we want, right. So I claim P is a maximal ideal in R. Okay. Now how do I do this? Okay. I have so I basically want to show that R mod P is a field. Okay. Now look at this R mod P. See, this is certainly an integral domain. So I have an integral I have an injection from here to S inverse R mod S inverse P, right. R mod P injects into S inverse R mod S inverse P, because R mod this is an integral domain. So therefore I have this extension. Now this is a field. Yeah, so this is a field. Yeah, K. Yes. See, again, you know, the trick goes back to the to say that this is yeah, this is a finite field extension. Okay, so this is, yeah, see, this extension is finite. Now this extension is also finite. Why is this finite? If I look at the generators of R, if R is generated by, let us say A1 over K as K algebra, then S inverse. So what we know is that R is a finitely generated K algebra, right. So this is a finitely generated K algebra. I want to say, sorry, yeah, then S inverse R mod S inverse P is a finitely generated K algebra as well, generated by A1 up to An and 1 by F. So therefore this is a finitely generated K algebra which is a field. Therefore by Nullstellens's weak form, this is a finite extension okay. That means this is a finite extension now. R mod P is an integral domain. You have this is a field that says R mod p is a field. Therefore, so this is R mod p is a field, that implies p is maximal. This is a finitely generated K algebra, okay, which is a field. Therefore, this is a, which one? This is a, why is it a finitely generated K algebra? That is exactly what I have written. If so, our assumption is that R is a finitely generated K algebra. Okay. So, if R is K, suppose I write this like this, then in fact S inverse R itself, S inverse R would be nothing but K A1 up to AN 1 by F. So here it is A1 bar up to. So S inverse R itself is a finitely generated K algebra, and here we are looking at S inverse R mod S inverse P. Okay. So this is a finitely generated K algebra, which is S inverse. This is a finitely generated K algebra, which is a field. This is finite extension, this is finite extension, this is field, therefore this is field. Okay. That means P is a field, sorry, P is maximal ideal, and that is exactly, and now that implies P is a maximal ideal with F not in P, because S inverse P is a maximal ideal, F cannot be in P. So that proves that radical I is intersection of maximal ideals. So another corollary is let I be an ideal in K x1 up to xn, K algebraically closed, then I of V of I is equal to radical of I. This is, in fact, we do not require I to be algebraically closed. One can prove this for any infinite field, and in that case there is a I mean there are, if you just search Google, there are a lot of proofs, different proofs using different techniques for this one. But there is a nice proof using Rabinovich trick, which I will leave it to you to check, read on your own, but I will write it as a corollary of this the earlier result. So suppose let f be in a radical of I, that implies that f power n is in I for some n. Okay. That means f power n, so I will write this point as, or okay, f power n A is 0 for every A in V of I. By definition, it is an element in I. What is the definition of V of I? V of I, those elements in I, those elements in Kn, those points in Kn, sorry, yeah, f is in, this means this is 0 for every a in V of I, and that directly implies that f power n no, so this okay, so this says that f power n of a is 0 implies that f of a has to be 0, because it is, you know, f power n of a is nothing but f of a whole power n, right. That means f of a is 0 for every a in V of I, and that implies that f belongs to I of V of I. So now let f be not in radical of I. If f is not in the radical of I, that means by earlier previous proposition there exists a maximal ideal x1 minus a1 up to xn minus an such that f is not in, so let me, f is not in M. What does that mean? See, I want to say that f is not in the I of V of I, this one, maximal ideals containing I, it has to be so. So here there exists a maximal ideal M containing I, such that f is not in M. Okay. Now see, M is contained in I implies that a1 up to an is in V of I, right. This point has to be in V of I, because every element is, see, every element in M is a polynomial combination of this. So if you put x1 up to xn equal to 0, that has to be 0. Therefore this is a1 up to n is in V of I, but now I want to say that I of f is not in I of V of I. Yeah, of course, yes. Yeah, this is C, and this is not in M implies that f of a1 up to an is non-zero, right, because f is in, I mean, this is characterization, f is in M if and only if f of a1 up to an is 0 for every a1 up to an is 0. So f is not in M implies f of a1 up to an is non-zero. a1 up to an is here and f of a1 up to an is non-zero implies that f is not in I of V of I. So that implies radical of I is equal to okay. So that finishes the proof for null Stirling's. So there is a weak form of there is another proof if k is infinite, need not necessarily be algebraically closed, then there is a proof using what is called Rabinowitz trick. You can search for this in or this proof is given in undergraduate commutative algebra by Miles Reed. Okay. I would like you to go through the proof. Okay. So, we stop here.